Hello students, welcome. We're about to jump right into one of the most important topics in SPM chemistry, the rate of reaction. In the next few minutes, we're going to cover everything you need to know to absolutely master this section for your exam.
But hey, before we get started, I want to share something super useful for your revision. To really make what you're about to learn stick, you should check out the MCQ SPM website, or just download the app. It's packed with past year questions, so you can immediately put what we learned today into practice.
All right, let's do this. In this first part, we're going to build a really solid foundation. We're going to connect the chemistry that's in your textbook to things you see and do every single day.
So let's start with a really simple question from your kitchen. The answer actually holds the key to a core chemistry concept. And yeah, it's all about the rate of reaction.
Okay, let's actually step into the kitchen, because chemical principles are at work all around us in there. Seeing these ideas in a place you know so well will make them way easier to remember when you're sitting in your exam.
Think about it. When you slice up a potato or some meat, you're not just making it bite-sized. From a chemistry point of view, you are massively increasing the total surface area that's exposed to the heat. And more surface area means more places for the heat to make contact, which leads to a much faster cooking reaction.
And you know what? It's the exact same idea with medicine. When you chew an antacid tablet instead of just swallowing it whole, you're breaking it down, right? This increases its surface area, which lets it react and neutralize stomach acid way faster, giving you quicker relief.
But it's not all about surface area. Temperature and pressure are also huge factors. Just think about a pressure cooker. It speeds up cooking like crazy because it increases both the pressure and the temperature, forcing those chemical reactions in the food to happen much, much more quickly.
Okay, now let's talk about a chemist's secret weapon for controlling reactions, the catalyst. This is a topic that you absolutely, positively have to master for your SPM exam.
So here's the key thing to get. A catalyst is basically a guide for a reaction. It shows the reactants a faster, easier path to become products. But, and this is so important, it isn't used up in the process. Its mass before the reaction is the exact same as its mass after the reaction.
I want you to imagine a chemical reaction needs to climb a giant energy hill just to get started. We call this hill the activation energy. Without any help, it's a really slow, difficult climb, and that's why the reaction happens slowly.
And this diagram shows you exactly what a catalyst does. It doesn't try to force the reaction up that original steep hill. Nope. Instead, it creates a brand new, easier path, a shortcut with a much lower activation energy. And because that hill is smaller, way more reactant particles have enough energy to get over it, and the whole reaction just speeds up like crazy.
Okay, everybody, listen up. This is a classic exam trap, and so many students fall for it. Do catalysts increase the activation energy? The answer is always no. You have to remember this. A catalyst's entire job is to decrease the activation energy. It makes the reaction easier, never, ever harder.
So this slide right here, this is what you need to memorize. These are the 4 key properties of a catalyst. If a question in your exam asks for the characteristics of a catalyst, these 4 points are your perfect answer for full marks.
All right, now let's scale things up. Catalysts aren't just for school labs. They are the powerful engines driving huge industrial processes that literally shape the world we live in.
A perfect example is the Haber process. It uses an iron catalyst to combine nitrogen and hydrogen to make ammonia. Now, why is that such a big deal? Because that ammonia is the main ingredient in fertilizers that help feed billions of people all over the world.
And then you've got the contact process. This one uses vanadium 5 oxide as a catalyst to produce sulfuric acid. Sulfuric acid is a massive deal in modern industry. It's used to make everything from car batteries to detergents.
You can even find a critical catalyst right inside your family's car. The catalytic converter uses precious metals, like platinum, to instantly change toxic exhaust fumes into harmless gases like carbon dioxide, nitrogen, and water vapor. Pretty cool, right? Okay, now for the part you've been waiting for, applying all this knowledge to score marks. Let's break down exactly how to confidently solve actual SPM questions on this topic.
When you see a graph like this in your exam, the first rule is do not panic. There's a really simple method to figure it out. The most important thing you need to look at is the steepness or the gradient of each line.
Just follow this 3-step process. 1. Analyze the graph. Curve P is steeper, right? A steeper curve always means a faster reaction rate. 2. Remember the factors. What speeds up a reaction? Higher temperature,
a catalyst, or more surface area. 3. Match them up. In this case, any of those factors would cause the faster reaction shown by curve P.
Now let's look at the other really common question style for this topic. This is an energy profile diagram, and it's designed specifically to test if you understand that activation energy hill we were just talking about.
And again, a simple 3-step method makes this easy. Step 1, find the activation energy. It's always the peak of the hill, which is labeled E3 on this diagram. Step 2, remember the catalyst's job. Its only purpose is to lower that peak. So, step 3, find the answer. The correct option will always be the one that says the catalyst decreases E3. It really is that straightforward.
So, the biggest thing to take away from all this is that this isn't just a topic for your exam. Understanding the rate of reaction is a core principle that chemists and engineers use every single day to solve huge, real-world challenges.
So I'll leave you with a final thought. Scientists are constantly searching for new catalysts. What huge global problem do you think the next big discovery could solve? Could a new catalyst help us turn plastic waste into fuel, or create clean hydrogen energy just from water? The future of chemistry is full of some really incredible possibilities.